Welcome back to OCR and MEI Further Mathematics B. Today we're doing chapter 8.1, Hyperbolic Functions. So hyperbolics are one of the new concepts that you need to get hold on during A-level. It used to be an FE2 topic, at least I think, and most people don't actually use them unless you do further math, of course. So it is really useful in science, by the way. So it's kind of odd because it strongly correlates to the trigonometric functions. So we also call them hyperbolic functions or hyperbolics. Let's have a look. So and in trig, we have sine, cos, tan. So sine, cosine, tangent, where tangent is the sine divided by cosine. That applies for hyperbolics with sine with an H behind. It is pronounced shine. Do not ask me why. It's pronounced shine. So I'm gonna let's see. I'm gonna use red to. This is a pronunciation for shine. Then we have cos, just simply cos as the pronunciation. Then we have tang as our third. They are essentially, well, I can use the congruent sign here, kind of equivalent in a sense, because their equations do match up in some case. So let's have a look. The first thing that we need to know is that in sine, we already know that e to the z, take e to the minus z, all on 2i is sine. That's just simple, well, what we learned from De Moivre's and exponential form. You can cancel out everything and you'll get sine. The cosine is e to the z plus e to the minus z, all on 2, where z is a complex number, by the way. And finally, we have tangent, which is simply sine divided by cos, e to the z, take e to the minus z, all over e to the z plus e to the minus z. Okay, so here we have three different expressions on sine, cosine, and tangent. I messed up an I here, so there's an I below. So that would work as sine, cosine, and tangent. So we can call trigonometry complex because it oscillates and it's periodic. And I'm gonna get back to that idea during next chapter, which is chapter 9. So complex relates to correlation, but for exponential stuff or hyperbolics, we have real rather. Let's put real for these. So these are all real, and their expressions would be e to the x take e to the minus x all over 2. Do you see how those two kind of match up? Then cos would be e to the x plus e to the minus x all over 2. And again, you can see the relation. So rather than the complex number, we have a real number. And for the complex, I was removed from the equation. So that works. And for tang, same for tangent. we divide sine by cos, and we have e to the x take e to the minus x all over e to the x plus e to the minus x, and that would give us the algebraic expression of the function. So in this case, we have, let's see, so z in this case would be corresponding to sine of a complex and cos of a complex, tan of a complex, whereas this sine would be corresponding to the x, cos x, and tangent x. So that would be what these algebra mean. For the purpose of the exam or this course, you're supposed to know the algebraic expression of the sine cos tan expression in the form of this exponential, and remember that they are real for all values of for all real values of x. So if you put in a complex into the cos function, then let's say bad things happen, and the algebra would get really complicated very fast. However, it is also possible that if you have a complex, you can convert from trigonometry to hyperbolics and vice versa. So you can go ahead and experiment on that during your free time if you have too much time on hand. But it's out of spec, so you do not need to know that. Another thing that you need to know, which is a required knowledge, is that similar to the trig functions, we have identities to remember, which is cos squared x take sine squared x is always equal to 1. So this identity is important in a lot of situations, and you can prove that from the algebra that this actually works. So I think that's all that you need to know for hyperbolics, at least the simple hyperbolics. You are gonna use, similar to trigonometry, you're gonna use their inverse functions, and you're also gonna use their differentials. Let's actually talk about the differentials right here. So when differentiating sine, cos, and tangent, similar to how you would differentiate tangent, tangent requires you to use a either quotient rule, product rule, or whatever to carry out. So we can take that aside and just focus on sine and cos. So sine, conveniently, if you do the differential on the algebra, you will get e to the x add e to the minus x all over 2, or you go down to cos. So if you differentiate sine, you get cos. What about if you differentiate cos? Same deal, e to the x, then you have the minus 1 e to the minus x, which is just negative e to the x, minus x, all divided by 2, gives us sine. So you go back to sine. So essentially these two oscillates between differentials, and there are no negative sign to worry about, unlike the trigonometric functions, because obviously there's an I involved in the expression over on the trig side, and there aren't any i's in the hyperbolic side, so we don't get the oscillating negative signs. So yeah, that's all for this video. Essentially, there aren't much else to talk about, to be honest. The key thing to note about hyperbolics is that you will be able to, you'll have to be able to differentiate them and also use them for calculus, which I'm going to talk about in the next video. And for now, thank you very much for watching. If you have any questions regarding hyperbolics, do let me know in the comment section below. And if nothing else, I will see you on my next one.